Hello everyone and welcome back to a new video in programming the Finite Element Method using MATLAB. It's been a long time since we had one of those easier videos, and I can only tell you that things are gonna get easier from now on, unless we benchmark, of course, where it becomes stressed out again. But we are gonna be dealing with diagram generation, and we are not gonna finish this in one video, of course, it takes time. But today we're gonna lay the groundwork for generating diagrams. So before I start, of course, I want to give my reminders that this is part of a video series, theoretical and programming, linked on the top right, and that channel members have access to the source code. But if you're not a channel member, then don't worry, because every single line of code will be written in front of you, and you can write along and you will have the exact same code as mine. So with that being said, let's dive into this video. So sit back, relax, and enjoy the show. Now, before I start, I must explain to you what a line diagram is. Suppose you have a beam and you want to draw the bending moment diagram of the beam. So what you need to do is, of course, according to statics, you would draw the shear force diagram, and then you would draw the bending moment diagram, and that's it. Then you would have done it. A diagram is a collection of equations, because in the bending moment diagram, some regions are linear, some regions are parabolic, and even some regions might be cubic. So a diagram is a bunch of equations, every equation having its own region. For example, equation 1 from x1 to x2, equation 2 from x2 to x3, and so on. So it's a group of equations bound together, and we need basically to know the equations and the domains of the equations. Also, we might be interested in the absolute maximum and the absolute minimum of the diagram, as well as the location of the absolute maximum and the absolute minimum. So this is what a diagram is. Now we're going to program the diagram, and we're also going to program what it means to be a cubic equation. Because in the end, our highest value for the diagram equation is going to be a cubic equation. You would think, why that? The reason behind that is because our highest load function is a linear function. So it could be a trapezoid, meaning it's a function in x. And you know from statistics that the shear is the integration of the load, meaning the shear could be a function of x squared, and that the moment is the integration of the shear. So the moment can be tops all the way up to the cubic equation. Of course, if we allow in our software to have a parabolic load, then we would need to increase the level of the equation to become a power 4 equation. Because if we allow for a parabolic load, then you would have a cubic shear and a power 4 moment. However, we are not allowing for a parabolic load. We are allowing to a maximum of a linear load, which means that we are safe in assuming a cubic equation as max. Today, we are going to build the basis of the diagrams and the cubic equation. It's going to be nice, not really that complicated shenanigans. So let's enjoy the show while it lasts. First of all, I must define what a diagram is. So I will go here to the plus. I will basically class dev me a line diagram and end my class dev, save, and call it line diagram here. It doesn't have an str here because I don't think it's a structural element. It's just a property of a structural element. And here inside it, there are multiple things. First of all, there's something called absolute locations 1. What I mean by this is the start of each equation, the domain of it. And then I have absolute, oh wait, I forgot. I should start with declaring properties, because those are things that the line diagram has, and methods are the things that the line diagram can do. So this is absolute locations 1, that's absolute locations 2. This is the end of each equation. And then I have, of course, the equations. That's self-explanatory. Equation of the domain. Then I also have critical values, absolute distance. By this, I mean location of critical values. Those are the max or min of the values of the equations. Then I have the location, which means also I need the values. And this is basically the value at that location. Also, I need the global maxima, minima values absolute distance. What I mean by this is I want one value that represents the absolute maximum value of the diagram, which is made out of multiple equations, I might add, and the value that corresponds to the minimum of the entire diagram of multiple values and equations. Here I will say a location of global maxima, minima. And here, of course, I will basically say global maxima, minima values, and this is values of global maxima or minima. Fantastic. Now, those are the things I would need for a diagram. Now, here for the methods, first of all, I need to have a constructor. So function object equals line diagram, and I'm gonna keep it as void. Nothing is needed here. In this case, I could init my stuff. I don't even think I need to initialize anything. Just leave it empty because they are initialized as empty. If this is a list, for example, in C#, I would basically say equations, for example, equals new, and then I would basically say list of cubic equations. However, we are not in C#, so this is kind of superfluous. MATLAB initializes everything to empty, which is exactly what I want. It's easier in MATLAB than in C#. Another thing I have here, another ability I want to have is something called function add diagram unit, because we are going to produce our diagrams and we want to be able to add new equations to the diagram. In that case, I need the object reference, I need the absolute location 1 and the absolute location 2, the start and end of the equation, and I also would need the equation. And in that case, I would just add those things into the storage system, meaning that object.absolute locations 1 is gonna equal the old object.absolute locations 1, added to it the new absolute location 1. Similarly, object.absolute locations 2, this is gonna equal the object.absolute locations 2 and absolute there we go. Finally, object.equations is gonna equal the old object.equations, and we're gonna add to it the new equation. So this is how we add a diagram unit. Fantastic. There seems to be a problem here. What gives? Value class method that modifies object must return. I forgot to inherit from handle. Yes. Now it works. Okay, so I need a function that calculates critical values. Now this is a to-do because you don't know what the cubic equation is so far, so this is a big to-do. And I need a function that basically evaluates. So here I need a function that basically is called evaluate. Let me here give output, or maybe a diagram value equals evaluate of, I need here to give it in capital, evaluate of object, and I need input the x. So I want a function that if I give it the x, it gives me the diagram value. So it will search for the equations and select the correct equation, evaluate the equation, and return it back to the user. So this is yet another to do here. So to do, I think here I should pass in the object reference because that's a function. This is a to do. Now it tells me error because it's not returning anything. That's fine, I'll do it later. And those are the things that my diagram should do. Now those are to-dos because I need to program the cubic equation first, and then I can dive into that thing. So yeah, those are diagram units, or line diagrams, sorry. Now I need to add a cubic equation because we agreed that the maximum thing that we can have in our program is a cubic polynomial or equation. So I'll go here and I'll class dev me something new. I'll call this cubic polynomial and end the class div and save. Wait, save. There we go. And now let's check out what the cubic equation is. It's very simple. Our cubic equation is ax cubed plus bx squared plus cx plus d. That's what the cubic equation is. So properties and methods. That's what we have here. So the properties, I basically have A, B, C is empty, and D. That's the only properties I need. And for the abilities, I would need a lot of things, by the way. Methods, and between brackets, static. I see. That's how it's done. I mean, in C#, you would basically say, for example, internal static void something something. But here in MATLAB, it's kind of different. Okay, fine. Now, static are things that not the object cannot do, but the entire family can do. So let's see. Now, first of all, for the normal methods here, an object must be able to initialize itself, so init itself, so it needs a constructor. Here, I'm going to basically call function object equals cubic polynomial of A, B, C, and D, because we must pass in the A, B, C, and D of the cubic polynomial. Fantastic. Now here in the constructor, that's very simple. I will go for object.A equals A, object.B equals B, object.C equals C, and object.D equals D. Fantastic. I have my constructor. Now another ability it must have is it must have the ability to evaluate itself. So here value equals evaluate me. And here I need to give the input object and x. So here a user can basically ask the cubic polynomial to evaluate itself by giving it an x. Of course, here the value is going to be a multiplied by x power 3 plus b multiplied by x power 2 plus c multiplied by x plus d. That's the cubic polynomial. Also, a cubic polynomial, as we will see, should have the ability to integrate itself. So here I'm going to return integrated polynomial, and this will be equal to integrate me. And when we integrate, we need initial conditions or a point of integration. So here I will give it an x0 and y0 to find the constant, basically. So we're going to integrate that dude. So in this case, okay, what do I know? What do I do? Now, first of all, I should make a check if, oh wait, I need object here. Now, first of all, if it's a cubic equation, then the user should not be able to integrating because I don't support power 4 equations. So here I would say if object.A is not equal to 0, because if I have a cubic equation, I cannot integrate it. I would basically say integrated polynomial equals object. I'm just going to prank him and give him back the polynomial. Okay? Okay. Now, I can integrate a square equation. So in that case, I'm going to basically have a new integrated polynomial, and in this case, this equals a cubic polynomial. And in that case, let me first of all init at 0. Let's initialize it to 0 first. And now let's start playing with things. Integrated polynomial.a, this equals b over 3. This is simple integration. Integrated polynomial.b, that's gonna equal c over 2. Oh, I should say object.b. And integrated polynomial.c, this should equal d over 1, or d, or object.d. And integrated polynomial.d, this is where the initial conditions come into play. This is y0 minus object, no, not object. Okay, let's do it here. Integrated polynomial.a multiplied by x0 cube minus integrated polynomial.b multiplied by x0 square minus integrated polynomial.c multiplied by x0. Let me just think about it. So in order to get the d, it must afford this function value. So y0, because this is the function, right? This is f of x. So y equals f of x. Now I need to find d, which means d equals y minus everything here. So y0 minus this, minus this, minus the, yeah, I think, yeah, those are the initial conditions. Now we do another ability. I will have a function here and I will call it derived polynomial, this, wait, am I returning it right? Yes. Derived polynomial equals derive me, basically. So we're going to derive the polynomial now. Now here we don't need anything, just derive me, because derivation is a reductionist value. So here it's actually much simpler. I would say derived polynomial is going to equal cubic polynomial of 0, 0, 0, 0. Now let's start doing things. So first of all, derived polynomial dot a is equals 0 because it's going to die. Derived polynomial of b is going to equal object dot a multiplied by 3 because it will be reduced to 1 power. I mean, think about it. What's the derivation of this thing? The derivation of this thing is going to equal 3ax squared plus 2bx plus c. That's what it means. So that's why we have 3 multiplied by a in the b slot, because now the a is going to be 0 and the value of b is going to be 3a and the value of a is going to be 0. Okay, that's the reason why we have this strange thing. So here, let's continue. Derived polynomial dot c is going to equal object dot b multiplied by 2, and derived polynomial dot d is going to equal c, or object dot c multiplied by 1. Why by 1? Because this dude becomes your constant. Fantastic. And of course now we should return, and we have done it. Yeah, that's good. I might even add the toString function here. So function toString of the object. Let's return something nice. Printf, I don't know, function of x equals 5.3 x cubed, sorry, plus 5.3. Oh, there is an f here. X cubed plus 5.3 fx plus 5.3. Now here we need to input the values, object.a, object.b, object.c, and object.d. I think I missed something. Yeah, there is an f here missed. Okay, so yeah, those are the abilities that itself has. However, there are outsider abilities that the class has, and those are the static abilities. So let's program them. Now, the static abilities here are two things, first of all. Function output, let me call it output now, equals add of. And here we're going to have a and b, where a is a cubic polynomial and b is a cubic polynomial. Notice, I don't need to pass in object because those are static functions. So in that case, output is going to equal a totally new, brand new polynomial, so cubic polynomial. Let's give it zeros as an initialization first, and then output. I know you could be more abstract and you can initialize those here, but I'm kind of lazy. Output.a equals a.a plus b.a. Look, if I have two polynomials, then I'm going to add the a of the first polynomial with the a of the second polynomial when I add them together. So output a equals the first polynomial. Maybe I should say P1 and P2 as in polynomial 1 and polynomial 2 to kind of make it look better. Now I can copy this entire thing and paste it 3 times. So 1, 2, 3. For some reason, the indentation is wrong, so let's fix that. This is B, that is a C, that's a D. This is a B, that's a C, and that's a D. Perfect. Yeah, I think that's that. Is there anything else? Yeah, we want to multiply those things, right? Or no? Yeah, I think we should be able to multiply. Now, we're not going to be multiplying polynomials by polynomials, but we may be needing to multiply polynomials by scalars. So here, I would have a function output equals multiply, and here I will put a scalar and P1. Okay, so there's a polynomial and there's a scalar. In that case, I'll just copy this entire thing. I shouldn't copy it. Let's write it. Output equals. So output.a equals polynomial.a multiplied by the scalar, and so on. This repeats for all the other sentences. So for all the other variables. So this is B, that's C, that's D. Of course, here all we have to do is to multiply with the scalar, and that's that. So I think we are good. Now, this is what a polynomial is. Wait, what's this? Oh, I think, what's that? I think I totally missed it here. This is object.a, and that's object.b capital, that's object.c capital, and that's object.d capital. I think that is a polynomial. Fantastic. Now we go back to line diagram, and we finish the stuff that we shifted for later. This is going to be a little bit awkward, but let's do it. So we have shifted for later the calculate critical values and the evaluate me. Okay. Now the evaluate me is kind of easier to do. Here we will need to first of all find which equation is going to be used. And how do I find that? Well, equation index in this case equals -1 first, and then I will loop for I equals from 1 all the way to the length of absolute locations, object.absolute locations, yes, object.absolute locations 2. So I'm cycling through all the absolute locations 2. Now I'm going to ask a question. If the object.absolute locations of 2 at the I is more than or equals the x, I should put an epsilon here somehow. You know what? I'm sick of putting epsilons here. Let's put it here. So if the end of the equation that are sorted, by the way, the equations are sorted. If the end of the equation is more than x, then that's my equation. I could add another condition and just put here object.absolute location 1 of I is less than x. Whatever. I think this is enough. If it's sorted, then it's enough. Okay, so in that case, I found the equation index. It's I, and I will break out of the loop. And now I'm going to use the equation. So here, if the equation index is not equal to -1, so we found it, then we're going to basically return something. Or you know what? Let's make a fail-safe mechanism. Although I should throw an error, let's make a fail-safe mechanism. So here, if equation index was indeed -1, I didn't found it, then I will make equation index equal the length of object.absolute locations 2. So I'm going to basically take the last equation. And with that being said, I will say diagram value equals, and here we're going to call in the equation. So object.equations at the equation index dot evaluate me, and we're going to pass in the x. It has been passed. Yes. Now this evaluate me is something we just programmed here somewhere. Where is it? Where is it? There it is. This one. Yes. So the evaluation, of course, because it's a diagram, we need to know exactly which equation to use. And that's something we have done successfully. Now, we need to do the final thing of a diagram, which is to calculate critical values. Now let's start with it. I will go here to the calculate critical values. First things first, I need to take every equation and get its maximum and minimum values. If it is a linear equation, there is an equation for it. If it's a quadratic equation, there is another one for it. And if it's a cubic equation, there is another one for it. So how do I find the absolute maximum and minimum? If we have a function, f of x equals something, and we want to find the maximum minimum values, what we need to do is to derive the equation and then set the derivative to be 0, in which case we find the x of the maximum and minimum, and from it we can find the values of the maximum and minimum. That is what I'm going to do. So here, for equation index from 1 all the way to the length of object.equations. And so now I'm passing through every single equation. For the start x value, I'm going to take absolute object.absolute locations 1 of equation index plus I think I need an epsilon here because I'm afraid of the evaluate mean. Okay, let's put an epsilon. Let me just copy this epsilon very quickly. And paste it somewhere here. Let me go to the line diagram here, call in properties, constants, and end. Wait, without s, constant end. And epsilon equals this, so I'm gonna use it now. So here plus line diagram dot epsilon, yes. And the end I will keep it as is. And wait, I cannot use end, it's a keyword, right? End dist. So start dist and end distance. This is object dot absolute small letter. Absolute locations to equation index, and that's it. Now here, first of all, for an equation, the critical values are, look, this is calculus now. Besides the derivative, we also have to check the start of the interval and the end of the interval, because those also might be maxima or minima. Object dot critical values absolute distance equals object, the old one, object dot critical values absolute distance and the start. Why not the end? Because the end will come, because we're going to cycle through the equations. Now here, I need to get a cubic equation. I will call it derivative equation. This equals the object dot equations at the equation index, but not it, but the derive me. Because I don't want the equation, I actually want the derivative. I programmed something called derive me somewhere. Let me see. Yeah, derive me. So here I will call in derive me. So now we are deriving the equation. Now here we need to, if we derive an equation, there are multiple possibilities. Possibility one, we have a quadratic equation. That's possibility number one. Because if the equation is a cubic equation, then the derivative is going to be quadratic. And now we need to solve for a quadratic equation. Now for the quadratic equation, let me first of all make a check for the quadratic equation. If absolute of d equation dot b, this is of course b here, let me remind you, the equation is ax cubed bx squared cxd. So b is the coefficient of x squared. A is always going to be 0 because we are deriving, and when we derive, we are reductionists. We are eliminating a. So here, if the d equation dot b is not 0, now let me say here it's more than line diagram dot epsilon, then we have a quadratic equation. That's true, but there is a danger here. The danger is that it's unsolvable. F of x equals ax squared plus bx plus c, right? And here you have a check that b squared minus 4ac is more than 0 for the roots to exist. Otherwise, you have imaginary roots. Now, unfortunately, our f of x here equals bx squared plus cx plus d because we are reducing from the cubic equation. So in this case, it's c squared minus 4 bd. That's the check. Okay, should be more than 0. So here I will get another check, and I will make sure that the absolute value of the equation, the derivative of the equation, c squared minus 4 multiplied by derivative equation dot b multiplied by derivative equation dot d, this entire thing must be more than 0, or in our case, more than line diagram dot epsilon. Yeah. Now, if that's the case, we have a quadratic equation that has roots. Okay? Because remember, we need to find the roots of the derivative to find the maximum of the equation. Else if, well, here I need to check if it is a linear equation, because maybe b equals 0. Okay? So else if here, to be a linear equation, it's going to look like this. It's going to be f of x equals cx plus d. That's what we have. So to be a linear equation, the c must be more than 0. Otherwise, it's a constant equation. So else if, and here comes, of course, the check, absolute of the derivative equation dot c is more than line diagram dot epsilon more than 0, meaning then we have stuff. Otherwise, do nothing. Do nothing, because if we have a constant equation, then it's the same everywhere, and I already added the start value, so the function value at the start is going to be the critical value. Okay, so here, I would say here we have a linear equation, so find its roots. And of course, at the end of this entire brouhaha, I must also add the end. So I'll copy this entire thing. Now you're wondering why am I where you might be wondering, why did I shift the end all the way until here? And by the way, that's a bug, because I want my equation to be sorted. Let's deal with the quadratic equation. The quadratic equation has two roots. We know this from mathematics. x1, remember now, the general equation of the quadratic root says that x equals minus b plus or minus square root of b squared minus 4ac and everything divided by 2a. Now our equation, unfortunately, doesn't look like f of x equals ax squared plus bx plus cx plus c. No, our equation is f of x equals bx squared plus cx plus d. So now we need to flip this in our mind, meaning that x1 in this case equals negative, I need a bracket here, divided by something. Now here I will divide by 2a, which is in our equation 2b, by the way. So here divided by 2 multiplied by derivative equation dot b. So we finished this part at least. Now we come here. So minus derivative equation dot c, because the b is our c in our equation. Then minus square root of, and here we can say derivative equation dot c square. Oh, it's actually this one. I can copy and paste it here. Yep, that's x1. I started with the minus here to make it smaller because I want to sort them. Now x2 is going to be the same equation but with a plus. So here I paste that, and here I have a plus, and that's that. Now I'm not going to add it immediately because I must make sure that this is unique. Maybe, I mean, what I'm saying here is maybe x1 is by strange chance the start value. I don't want to add the start value twice. So here, also another thing, I mean, okay, I can add the start value. I must make sure that x1 and x2 are within the interval, because you could have an interval, but the maximum values are outside of the interval, and you would not even be able to use them. So here I will go for if x1 is more than the start distance, minus epsilon because of shenanigans, diagram.epsilon, okay? And x1 is less than end distance plus line diagram dot epsilon. If that's the case, then we can add it. That's the thing. So here, if x1 is between the start and the end, then I can basically add it to the list. Again, I will do the same thing for x2, just to make sure that x2... Now, by the way, I didn't check if something like it exists, because I could have duplicate roots. But okay, fine. I mean, that's not a big deal. Now we finished the quadratic equation. Now we go to the linear equation, because it could be another case where I have a linear equation instead of a quadratic equation. So how does it look in the linear equation? It looks actually much easier. You see, in this case, x, the root, equals negative. I mean, here, look, let me explain this to you. F of x in this case equals cx plus d, right? If you want to set it to 0, then x equals negative d over c. That's it. That's everything you need. So x equals negative derivative equation dot d divided by derivative equation dot c. Fantastic. And now we can basically do the check again, the entire check here, because I need to make sure that the derivative is inside the place. So yeah, that is how we calculate the critical values absolute distances. But we are not finished yet, because now we need to get the values. So here I will go now again and I will create a for loop to evaluate. So here, for I equals from 1 all the way to the length of the object.critical values absolute distance. Now, by the way, I know this seems to be a long video, but in reality, it's actually easier than the stuff we have seen before. So I hope I don't get disheartened of this. In that case, I'm going to run through everything first. So here, okay, let me write here some commentary. So here, we finished finding the x values. Now, find the diagram values. So now we have the x values here. And now I'm going to basically go and say object.critical values. It might be too much. So let's say here x equals object.critical values absolute distance of I. So you get the x. Now here I will say val equals object.evaluate, evaluate. And we need to pass in the x. And then finally, we store the values. So object.critical values equals the old object.critical values added to it, the new value. Yes, this is how we store things. One final thing is, let's find the absolute maxima and minima. So how do I do that? Well, I will cycle through. First of all, let's define some stuff. Here, I will say minimum index equals -1, maximum index equals -1, minimum value equals infinity. Wait, does it work? Let me see. A equals infinity. So now I will say 5 less than z. Does it understand it? Yes. Okay, 5 more than z? No. Okay, now let me say z equals -infinity, a big negative number. So 5 more than z. Okay. 5 less than z. Okay, understands it. So here I would say inf for infinity, a big number. For max value, I'm going to go for the very small number, -infinity. This is typical programming stuff. Now I'm going to cycle through the values. So for I equals from 1 all the way to the length of object.critical values absolute low or distance. Distance, yes. Now here we need to check and ask a question. If the minimum value is more than object.critical values at I, so if this is less than this, then replace. And how do we replace here? We replace by saying minimum value equals the new minimum value, and the index equals I. Another question here for the max value. So here we do the same thing, paste, but this time it's called max value. And this is going to be called max index. And in that case, if the maximum value is less than what we have, then use what we have. Okay. Oh, this is min value. Fine. Okay. So now, yes, we finished this, right? Okay. Now let's ask a question. If minimum index is not equal to -1, so we found something. So if you have found something, then object.global maxima minima values absolute distance. Oh my God, this is so long. What a name. Equals the old one, and we add to it. That's a very, very long one. We add to it the new distance. So we take this, we put it here, and we take it at I. So we add the distance. No, not at I. At the this is distance, right? So we add the distance at the minimum index. Yes, that's true. What a command. Okay. And also, we copy this entire command now, or we just write it again. Object.global maxima minima values only without distance. In this case, we're going to add, so we're going to use the old global maxima minima value. What kind of a stupid name is this? Object.critical values at the minimum index. Yes. Now, otherwise, if you haven't found it, you're just going to add zeros. Okay. Now, The next one, if by some chance you have a constant equation, and in that case the minimum index is not equal. Now if we have a constant, it's equal. If you don't have a constant function, which should be the case 99% of time, then min index and max index are not the same, and I need to add again the entire thing, but this time at the max index. Oh my, that is a long command. Yeah, I think we've done it. I think that's everything the diagram should be able to do. Yeah. So yeah, I think that's everything I wanted to talk about today. It might be a long video, but it's not really that hard. It's actually one of the easier videos about the logic. It's just preparing some objects for later use, because we need to program diagrams. So yeah, that's everything I wanted to talk about today. I hope you enjoyed. And in the end, I want to give a line diagram sized shout out to my dear channel members in the contributor level and the helper level, whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support to the channel is priceless to me and enables me to provide you with videos hopefully on time and with the certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on, especially subscribing, because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel. I will catch you in the next video. Bye bye.